Physical Science. This is Mr. B, and we are starting Chapter 4 today, and the title of this chapter is Atomic Structure. And remember, when we say the word atomic, we are talking about what is called an atom, which hopefully I think almost all of us have heard of, and a very small, tiniest, basically thing that as scientists can study at the smallest possible level. We are all made up of atoms. So what we're going to take a look at in this chapter is actually how an atom is set up. And so the title of section 1 within chapter 4 is Studying Atoms. So what this section is going to take a look at is some of the early work that was done to help us understand what an atom is, kind of how we got some of our first ideas, and hopefully maybe some of these names we're going to see might be familiar to some of you from the little timeline project that we did. So to start off here, it makes a little comparison between atoms and the wind. So it says studying the structure of atoms is a little like studying wind. Because you cannot see air, you must use indirect evidence to tell the direction of the wind. Atoms pose a similar problem because they are extremely small. Even with a microscope, scientists cannot see the structure of an atom. And so that's why, if you remember, we did the activity in class with the brown paper bags where you had to determine what was inside of them without actually being able to see what it was. And it's kind of the reason why we did that is to put yourself in the shoes of these early scientists, because they had to use indirect evidence to kind of help them understand what was going on. Because again, we can't just take a piece of gold, zoom in on with a regular microscope and see the atoms. They're so small that does not even work. And so to start, we're actually going to go all the way back to ancient Greece. So ancient Greece is where people first started trying to explain what an atom was. So in ancient Greece, they're kind of going to tie it in right here with this question right here. So it starts with a question. It says, if you cut a piece of aluminum foil in half, you have two smaller pieces of the same shiny, flexible substance. You could cut the pieces again and again. Can you keep dividing the aluminum into smaller pieces? And Greek philosophers debated a similar question about 2,500 years ago. So they're basically just wanting to know, how small can you actually make a substance? And if we start with a substance and we keep cutting it in half and cutting it in half and cutting it in half, how small can we go before maybe either it eventually turns to nothing? Is there a point to where it just stops and to where it can no longer be divided? Is there one point to where we get to a substance of matter and say this is as small as it goes, can't go any smaller than this, or can we keep dividing it up? So there were a couple conflicting ideas early on about this question. So the first one, or our first explanation, came from the philosopher. His name was Democritus, and I would definitely write down some things about Democritus. He was an important character here. He believed that all matter consisted of extremely small particles that could not be divided. He called these particles atoms, from the Greek word atomos, which means uncut or indivisible. So this guy in ancient Greece, and I believe this was about 400 BC is when this was going on, so this is very, very early in human history. He actually had it right. Again, he didn't really have much of an explanation for how these things were made up, about their structure. He just knew that they were there. So he called these particles atoms, which is what we still call them today because it means, in Greek, uncut or indivisible. So he had it right way back when. He may not have gotten the credit, as we're going to see here in our next one, about what most people believed, but he actually had it right. But he did not actually know exactly what an atom looked like. He just, well, I guess he thought that there were small particles that could not be divided, which again ended up actually being proven correct, but we're going to see here in a little bit that it wasn't until many years later till that was actually accepted. So Democritus, very important guy. Again, he had the general idea there, but maybe didn't have the support that he really deserved. The one that got the most support way back when came from a guy known as Aristotle, so I'd make sure we have something written down about Aristotle. And he thought that all substances were made of only 4 elements: earth, air, fire, and water, and he did not think there was a limit to the division of matter. So he thought that we could just constantly keep dividing things, keep dividing things, keep dividing things forever. He didn't think there was a point that we could reach where we could stop dividing it. He thought everything was just made up of earth, air, fire, and water. And kind of what this little picture here means is that he believed air was a combination of either being wet or hot, water was either going to be wet or cold, earth was going to be cold or dry, fire was going to be dry or hot, just kind of depending on the scenario. So that is kind of what this little picture means here. That's kind of how he explained matter. And for many centuries, most people actually accepted Aristotle's view on the structure of matter. So again, this was around, again, maybe 200 or 300 BC, maybe even a little bit later in 400 BC. This was an accepted belief. And by the 1800s, however, scientists had enough experimental data to support an atomic model. So this was kind of believed until the 1800s. This was the main belief going on here. So it wasn't until, again, just a couple hundred years ago where people started to say, okay, maybe Aristotle wasn't right. Maybe there are these tiny little structures out there that cannot be divided up into any smaller pieces. So our first important character in the 1800s was a guy by the last name of Dalton. So he's another important guy, John Dalton. I think we'll get his first name here in a second. And what he did was he proposed the theory that all matter is made up of individual particles called atoms, which cannot be divided. So he made an official claim here. Again, Democritus was the first one to kind of have this idea. Again, it was way, way, way long ago. No one really believed him. Everyone kind of supported Aristotle. So Dalton is kind of trying to reinvent and restate what Democritus said. So John Dalton studied the behavior of gases and air. So this is going to be kind of how he stakes his claim into atoms here. And based on the way gases exert pressure, Dalton correctly concluded that a gas consists of individual particles. So remember, we just talked about this in our last chapter. The reason why we feel gas pressure in a closed container is because particles are making collisions with the wall. So Dalton was one of the earliest scientists who kind of was able to figure out that gases were made up of individual particles, that there had to be collisions occurring to cause the pressure inside our closed container. So what Dalton did then was he measured masses of elements that combined when compounds form, and so the ratio of the masses of the elements in each compound was always the same. So when hydrogen and water combined together, for an example, he would say that there's always the same amount of hydrogen, there's always the same amount of oxygen, and they're always attached in the same way. No matter what, no matter how many water molecules there are, whether there's one or a million, every single one of those compounds is going to be attached in the exact same order, and it's going to have a fixed composition right here. So in other words, compounds have a fixed composition. Same thing like with salt. So the way salt is made up, it's always going to be the same amount of elements in there, and they're always going to be attached in the same order. So that was in another one of Dalton's early contributions. And again, this is just another example of what I just said. So it says when magnesium burns, it combines with oxygen and magnesium oxide. The ratio of the mass of magnesium to the mass of oxygen is always about 3 to 2. So magnesium dioxide has a fixed composition. So that means that for every 3 magnesium, there's going to be 2 oxygen. That's basically all it's saying. And so if we're talking about H2O, for every 2 hydrogens, there's 1 oxygen. So this is just another kind of a real-life example of how compounds form in a fixed composition here. And so then our next, let's see how many we have here. So our next 3 is going to just kind of sum up what Dalton did. So these, I would make sure I jot these down because these are all of Dalton's main points in his theory. So he said that all elements are composed of atoms. Says all atoms of the same element have the same mass, and atoms of different elements have different masses. So it's saying all gold is going to weigh the same, and it's going to weigh different than silver. So gold and silver atoms are going to weigh different from one another, but all the gold will be the same, and all the silver will be the same. It says compounds contain atoms of more than one element, and in a particular compound, atoms of different elements always combine in the same way. So this was these were his main points right here. Again, most of them pretty correct, and then some of them we're going to see might need to be revised here later on, but I would make sure I wrote all of those down. And to help understand his model, Dalton made these wooden spheres to represent the atoms of different elements. A tiny solid sphere with a different mass represented each type of atom. So if you were had more mass according to Dalton, you're probably going to have a bigger sphere. If you were a smaller atom with less mass, you're going to have a littler sphere. And so the reason why to kind of wrap this up, we can call this an atomic theory, is because if you remember from our definition from early on in the year, it says a theory must explain the data from many experiments. And because Dalton's atomic theory met that goal, the theory became widely accepted. And over time, scientists found that not all of Dalton's ideas about atoms were correct. They revised the theory to take into account new discoveries. So Dalton didn't have everything completely correct, but that's completely fine. A theory does not have to be 100% correct all the time. We've learned that, again, if it was a 100% correct, they would have called it Dalton's atomic law. But it is a theory. Again, it brought together the data from many experiments and has the ability to be revised. So that is why it is classified as a theory. So that is it for our first part of section 1. Let me know if you have any questions.